Hello, today we're going to be comparing the means of two independent samples. This is the most common situation when you have two groups and you want to determine whether the means are different or not. You will need SPSS 19, you will need the data file laphernia.sav. There's no new core reading this week, it's just the t-test chapter which you should have read last week. In fact, there is no new concepts to introduce this week, it's just the same as we did last week. So hopefully you won't find this as difficult as the last video was. We will be using the functions explore, and this is an excellent way to use this function. I think you'll really get a hang of using this. We will be comparing means in two different ways. The first is a parametric test that requires normally distributed data using an independent sample t-test, and the second does not require that assumption. It's a non-parametric test to compare two means, and it's called a Mann-Whitney U-test. Opening lap.hernia.sav, you should see this. Go to Analyze Descriptive Statistics, Explore. Now previously we pulled just our dependent variable into the dependent list. Now we also want to include a factor, and the factor that we're going to look at is laparoscopic. So the question we're asking is, if someone has a laparoscopic versus an open hernia repair, is their pain score different afterwards? Go to statistics and ensure that descriptive's confidence interval for mean 95% is ticked. Go to plots, untick stem and leaf, and tick histogram, leave everything else the same, and click OK. The explore function gives you the basic data first of all. So now we have laparoscopic yes and no, and pain score. We can see the numbers in each group and whether any are missing in each group. The descriptives gives us means, confidence intervals, standard error of the means, things we should all be familiar with now, but split between the two different groups, so the no group and the yes group. So what we're suggesting here is that the laparoscopic no, the opens, versus the laparoscopic yeses are two different populations of patients, and we have sampled those populations of patients with the data that we have in this data set. So we can see in the open group that the mean pain score is 5.43, and in the yes group the mean pain score is 3.5. So there already seems to be a difference between the two groups. What about the variability in the groups, the dispersion, the variance and the standard deviation? Remember, standard deviation is just the square root of the variance. So the standard deviation in the open group is 1.19. The standard deviation in the yes group is 1.61. So these are slightly different. I'm just skipping on down to the plot at the bottom of the output. This is a box plot. These are excellent and convey a lot more information than a standard bar chart does, even if the bar chart has an error bar on it. I would highly recommend using these in lots of circumstances. This is really your 5-number summary. This is why we hammered on about this so much at the beginning. So in the middle you've got this line which is in the median. The box here is the interquartile range, and the whiskers, sometimes called a box and whisker diagram, is the range. Although there is a rule that if the range is greater than a certain, usually 1.5 times the interquartile range, then you have extra stars included which just mark outliers above and below the range. So it's not always entirely the range, but in this circumstance it is. So this gives us lots of information. We can make a judgment here about the normality of the data. So on the no plot here, the box does seem to be slightly lower towards the lower part of the range than the top, which may suggest that it's slightly right skewed. The skew is going up the way. On the yes, this looks much better, although the median is not quite in the middle of the interquartile range. Anyway, so you can use those to make a judgment. Now, two of the requirements of a t-test, the first one is that the data is normally distributed, but the second is that the variances are the same between two groups that are being compared. So we've already looked at the standard deviation and shown that they are slightly different. And this box plot allows you to make a judgment as to how close the variances are. Again, it's a bit like when we were looking at the QQ plot. What is too much difference in the variances or the standard deviations between them, what is normal, what is not normal. And that is just a kind of judgment which comes with time. Statistics is an art after all, not a science. Let's go back and look at the histograms. The histograms are now produced for each independent group within your data. So this is the laparoscopic no, the open group. Is this normally distributed? It doesn't look particularly good for being normally distributed. What about the yes group? That looks much better and looks not bad for a normal distribution. We can actually go back and include some QQ plots. So let's go back to Analyze, Descriptive Statistics, Explore, and go to plots, but this time include normality plots with tests here. And click Continue and OK. And this will produce all our plots again, but this time we've got normality plots included. Actually, this isn't as bad as we might have feared. There is slight deviation towards the right-hand side of the graph from the 45-degree line, but it's not bad. And for the yes group, again, they're hugging the line there. That looks quite good. Looking at the D-trended graphs, so you're just looking at there's no pattern above or below the line here. There doesn't seem to be a particular pattern there on the no. On the yes, are there maybe more below the line and more above the line here? But again, they're not bad. So I would say, despite that dodgy looking histogram for the no group, for the laparoscopic no group, I think you could probably get away with doing a t-test here. The requirement for normality and the requirement for equal variance for a t-test is not quite as strict as people make out. For ANOVA, which is another technique for comparing multiple groups rather than just two, then these conditions are much more important than they are for a t-test. But a t-test is a good test and it's reasonably robust to deviations from normality and reasonably robust to differences in the variance, differences in the spread, in the standard deviation between the two groups. So let's go ahead and do a t-test. Analyze, compare means. Independent sample t-test now rather than one sample. We're wanting to look at pain score and we're wanting to compare laparoscopic. Define the groups. The groups are 0 for no and 1 for yes. That's what we defined them as earlier. You can check the options, there's nothing to change there, and click OK. So here's what you get. As before, you get the descriptive statistics, but this time it's split into your two groups, which shows the mean, and there appears to be a difference in the means there, the standard deviation and the standard error of the mean, which is, as you know, the standard deviation divided by the square root of the number in each group. Looking at the t-test itself, there's two different lines that SPSS gives you for a t-test of independent samples. The first, as you can see, are equal variances assumed, and the second is equal variances not assumed. In general, you should use the top line. But where you might want to be cautious is if you had a significant result when equal variances were assumed, but a non-significant result when equal variances were not assumed, particularly if you were worried that there was a difference between the two groups. I hope we're clear now about what we're talking about in terms of these variances. So a population can be, or a sample is defined by its mean and its spread. The spread has lots of different ways of characterising the spread. The variance is one, square root of the variance is called the standard deviation. These are effectively the same number because they're just a factor away from each other. So equal variances means that the spread of the values in the two different groups are the same. So what is an independent sample t-test doing? Let's sketch it out. So here are our two populations. and they're roughly normally distributed, and one has a mean of 5.4, and the other has a mean of 3.5. And this is pain score, and this is frequency, or more correctly, density. I can't really write with my mouse very well, sorry. Now, from our knowledge of the standard error of the mean of these two samples, we can make an estimate of how likely these means are to represent the population mean. And because of that, we can make a judgment as to how likely it is that these two different sample means are really just from the same population, or that the difference between them is 0. So we're asking, what is the probability that the difference between these two sample means is 0? Or what is the probability that they're different from 0? So this is one population minus the other population. And the difference between them is 1.9. We don't know what direction that difference is, so we need to do a two-tailed test because we don't know the direction. And we're asking what is the likelihood that the difference between these populations is 1.9 or greater. This is what a t-test does. Back to our output box in SPSS, and it's similar to how it looked before. So we can see the mean difference here, 1.9, and the standard error of that difference. So that's the only thing that we're doing differently this time. We're actually calculating a standard error of the difference, and the details of that don't really matter, but that's what you divide the mean difference by in order to get your t value. We can do it by hand if we want to. This is beyond what is required, so don't worry about this, but I think the equation for it might be in statistics at square one, but it is just the variance of the first group, 4.38, divided by the number in the first group, which is 21, plus, I'm using a bracket, the variance in the second group, which is 2.584, divided by the number in the second group, which is 29, and then the square root of that, which is 0.3969. 3970. So we're correct with that. And why do we do that? Well, if you think about it, the variance divided by n and the square root of all that is just the same as the standard deviation divided by the square root of n, because the standard deviation is the square root of the variance. So have a think about that. Variance divided by n, square rooted, is the same as the standard deviation divided by the root of n. Wow, well, how much does that not matter? Sorry. So what does it tell you? Well, it gives you a t-value of 4.807, which is associated with a significance level sig two-tailed, which is the p-value of effectively 0. What does that actually mean? Let's go back to our graph here. This is really our null hypothesis, which is suggesting that there is actually no difference in the population means between our two groups. So although we have sample mean of 5.4 and a sample mean of 3.5, the actual difference between the population means is 0, and that's represented by this graph. So if that was the case, if the difference in our population means was 0, what is the likelihood, what's the chance, what's the probability of finding a difference between these two samples of 1.9, given the standard error of the mean, which is the variation in the groups? And that probability is represented by these red hatchings, by this red shaded area. And we've shown that the probability of having a difference between our two samples of 1.9 or minus 1.9 is effectively 0. So that allows us to very confidently reject the null hypothesis, which is there is no difference between the groups. I hope that makes sense. I hope you understand that. We're just going to finish off now by looking at the non-parametric equivalent test. Now, the circumstance where we would use that is if we weren't confident that we had a normal distribution between the two groups. Now, it's important because the non-parametric test is not as good a test as the t-test, and you're more likely to miss a difference between the two groups. And this is type 2 error, which will come up in the future video. You're more likely to miss a difference that exists between the two groups with a non-parametric test, so you should use a t-test where possible. But if the normality assumptions were much more greatly disrupted than they are here, you might choose to do that, and I'll just show you how to do it. So go back to the data, analyze, down to non-parametric tests. Now, in this version of SPSS, you now have a kind of fancy interface that you can do it with by hitting independent samples there. I find that actually quite complicated to follow, so I would suggest using the traditional 2 independent samples, which is under legacy dialogues, 2 independent samples, and that will give you a similar box to the t-test box. Scoot pain score over, scoot laparoscopic over, define the groups as we did before, 0 for no, 1 for yes, and the test we're going to use is called a Mann-Whitney U test, and you just need to hit OK, and that gives you these boxes here. Now, the Mann-Whitney U test, I'm not going to get into it in a lot of detail because the details of it don't matter, but combine the two groups and rank them from 0 to, in this case, 50. And where the two, so that's in the combined groups, so pain score of no, yes are all combined, and you just put the pain score in order from the lowest to the highest. Then you number each of those orderings, 1, 2, 3, 4, up to 50. Then you take the mean, these details don't matter, but then you take the mean of the ranks. So if pain score is higher in one of the groups, then you'll expect the ranks to be higher, as is the case here. And then you use that to do a statistical test, and this gives you a p-value out the other end, which is, again, effectively 0. So this result confirms what the t-test result is, that we can reject the null hypothesis that the difference between these groups is 0. So what I'd like you to go away and do now is determine whether there are a difference between those in the recurrent versus not recurrent groups in terms of pain score, and whether there's a difference for gender. So do males or females have a higher pain score after hernia repair? Any questions to the boards?